Hello everyone, my name is Chemino and today I will be presenting our research on a monocular depth-based fusion method to address occlusions and low confidence regions in SGBM. Here is the outline for our presentation. First, I will start with the introduction, covering the background and motivation for our research. Then I will explain our proposed method in detail. After that, I will present the experiments and their results, and finally wrap up with our conclusion. As you know, 3D perception is crucial for future industries like autonomous driving and robotics. One of the most fundamental ways to achieve this is through stereo vision. The basic workflow involves capturing two images from slightly different viewpoints, computing the pixel-wise positional difference, known as a disparity map, and then converting that disparity into a 3D depth map using camera geometry. For this process, we use SGBM or semi-global block matching as our core technology. It is a representative stereo matching algorithm well known for its optimal balance of accuracy and speed. As this diagram shows, SGBM follows a sophisticated three-stage process to create a disparity map. However, despite this sophisticated process, SGBM is not perfect when it encounters challenges with conditions like occlusions, low texture surfaces, or repeating patterns. It fails to find reliable matches. This failure manifests as two critical errors in the final map: large holes, which are areas with no data, and low confidence regions, which are noisy and inaccurate. As you can see in the SGBM result, these errors prevent the generation of a complete and reliable 3D map. To address SGBM's limitation, we turn to monocular depth estimation. As you can see, the monocular result from MIDA successfully fills the holes where SGBM failed. However, it comes with the own critical weakness. It lacks an absolute metric scale and tends to lose fine structural details, resulting in an overly smoothed map. These complementary strengths and weaknesses are the core motivation for our fusion approach. Now I will explain our proposed method to solve this problem. This diagram shows our overall pipeline. First, in step 1, we acquire a rectified stereo image pair in our input. Then, in step 2, we perform estimations in parallel. One pass uses SGBM to compute a disparity map from the stereo pair, which is geometrically accurate but contains holes. The another pass uses a monocular model, MIDAS, to infer depths from a single image, which is dense but lacks an on absolute scale. The outputs of these two parallel processes are then fed into our core fusion stages, which I will explain in detail on the following slides. The next step is to resolve the scale inconsistency. The monocular output is only a relative depth map. To align it with SGBM's absolute scale, we apply a least squares fitting method. This estimates a scale and shift factor, transforming the monocular map into a new aligned map that shares the same domain as the stereo result. Now I will show for the final step of our pipeline, fusion and hole filling. The logic here is very straightforward. We want to preserve the high accuracy of the SGBM data wherever it is reliable. We only use the monocular data as a patch to fill in the gaps where SGBM failed. The logic is implemented with this simple conditional formula. For each pixel, we check if the stereo disparity value is valid. If it is, we keep the original SGBM value. If it's not, meaning it's a hole, we replace it with our aligned monocular result. By doing this, we create a complete disparity map that preserves the accuracy of SGBM while levelizing the robustness of monocular estimation. Now, let's see how this method actually performs in our experiment. Now, I will show you our result on the Middlebury dataset. This is the representative success case. If you look at the stereo SGBM result, you can see it captures the structure of the flower well, but it has large holes and a high RMSE. In contrast, the monocular Midas result has no holes, but the flower shape is overly smoothed with the low RMSE. Our fused result effectively fills the holes from the SGBM while restoring the fine details that Midas lost. As a result, it achieves the lowest RMSE of 15.1, demonstrating a superior performance both visually and quantitatively. However, our method has limitations. In this case, the initial SGBM error was extremely large with an RMSE over 225. Our simple hole filling method was not sufficient to correct such a massive error, and the final fused result was still highly inaccurate. This shows that our method is dependent on the initial quality of the SGBM output. We observed another limitation on the ETH 3D dataset. Here, SGBM already performed exceptionally well. In contrast, the Midas model, which was not trained on this type of data, produced very poor and noisy result. When we fuse this, the noisy monocular data actually slightly degraded the final performance. This highlights that the generalization capability of the monocular model is a critical factor for successful fusion. To summarize our finding, our discussion highlights three key limitations. Our simple fusion method cannot address low confidence regions. The monocular model has generalization issues, and our work lacks real-world validation. However, our conclusion is that we have presented a practical solution to the whole problem in SGBM, achieving a better balance between accuracy and robustness. For future work, we plan to address the limitations by developing a dynamic fusion method using confidence maps to handle low confidence regions, and also pursuing model lightweighting for on-device implementation. This concludes my presentation. Thank you for your attention.